So, good evening, everyone, and I welcome you all to today's live session for the course Elements of Mechanical Vibration, NOC25-AE17. I'm Rashi Aditi Ranjan, NPTEL PMRF TA from the Department of Mechanical Engineering, IIT Patna, and we are into the week 6 live session for this course. We have already completed 5 live sessions up till now, wherein we have discussed several kind of questions that would be helpful for you to solve the assignment problem. So, for this week, I hope everyone has gone through the lectures till now. So, for this week, basically, the idea of this week's lecture was basically based upon how are we going to find the solution of our system when we have a periodic forcing onto the system. Up till now, we were discussing about harmonic oscillations, harmonic forcing, and then we discussed about impact. If for a very small time, a large amount of force is applied on the system, then how our system is going to respond. But this week, we discussed about how the system is going to behave if there is a periodic kind of forcing onto the system. So, you all know what we did when we were solving the questions as it was discussed in the second, yes, as it was discussed in the in some of the questions that were there that the professor discussed in the lectures. So what basically we were doing was, if we have some forcing of the form f f1 cos of omega 1t plus f2 cos of omega 2t. What we were basically doing was we found the solution for this, let us say x1 of t. Then we found the solution for this, which was x2 of t. And then the total solution x of t was written as x1 of t plus x2 of t. But this is applicable only if our system is linear. Okay, only if our system is linear. But why is it so? I mean, why are we applying this only when we are discussing about a linear system? How about how do we deal with the nonlinear system? Anyways, dealing with a nonlinear system is not in the scope of this course as of now, but the question is that if we are applying the superposition rule, so this is basically the superposition rule where what we are doing is we are finding solutions corresponding to two different forcings, and then we are simply adding those two solutions to get the total response. But the question is that how do I know that whether my system is actually in the range such that this kind of a solution can be found out, right? So basically, the question says that is the superposition rule applicable to a simple pendulum? So the first thing is, what is superposition rule? Superposition rule basically constitutes of two major rules. First one being the first one being the homogeneity rule, which says that if I have x of t as my input to the system and I get the output as f of t, then by the homogeneity rule, this relation which holds between x of t and f of t, which we can say could be a acceleration equation, right? Wherein, like in case of a duffing oscillator, not duffing oscillator, actually spring mass dashpot system, we have mx double dot plus cx dot plus kx dot. So x is going to be our input. We are going to perturb the system, and then the system is going to oscillate. Using that equation only, we are solving it and getting the solution. So if x of t is going to give me a behavior which is of the form f of t, then alpha into x of t should give me alpha into f of t. So if I'm multiplying my input with alpha, my output should also be multiplied by alpha. that this is the only change that is going to happen. Okay. The second part is additivity. Now, additivity says that if x1 of t is giving me a solution f1 of t, x of t is going to give me a behavior of the form x2 of t, then x1 of t plus x2 of t is going to give me a solution of the form f1 of t plus f2 of t. So similar to what we were doing, okay, how it was discussed in the lecture. Okay. Now the question is that okay, this is fine. I know that this is applicable, but how is it true for our system, isn't it? So if the question is about a simple pendulum, and if I talk about the equation of a simple pendulum, it is theta double dot plus g by L sine theta is equal to 0, right? This is the main equation for a simple pendulum. Now, if I assume that theta is very small, we can replace sine theta by theta, and then we can see that both additivity and homogeneity rule are applicable to my system, right? But how about if I still have sine theta in the system? Then what is going to happen, right? So if you look over here, you can see that theta double dot is equal to what? Minus g by L sine of theta. Now, if I want to know what is going to be the solution, if I replace theta with alpha theta, it will be minus g by L sine of alpha theta, which is not equal to alpha into theta double dot. So it is violating the homogeneity rule. Similarly, if I check, let us say theta 1 double dot is equals to minus g by L sine of theta 1, and theta 2 double dot is equals to minus g by L sine of theta 2. So if I replace theta with theta 1 plus theta 2, then we get nu theta n double dot is equal to minus g by L sine of theta 1 plus theta 2, which is not equal to theta 1 double dot plus theta 2 double dot, right? So but now if I take sine of theta is very, okay, I'll just write it in mathematical form. It is very less than 1, then sine of theta is nearly equal to theta. In this case, my equation becomes theta double dot is equals to minus g by L theta. Now you can clearly see that this satisfies both the homogeneity rule and the additivity rule. So if I am told to find out a solution for a simple pendulum, then I can use the concept of x1 of t plus x2 of t if and only if and only if theta is small. If theta is larger than the particular value, then this will not be applicable. Then this will not be applicable. So in this course, since we are mostly concerned about linear system, we will be using the superposition rule to find out the solution. But I thought of discussing this question because we should have an idea about what we are doing in this course, or specifically for finding out the solution for periodic forcing. It is applicable only up to a certain limit for a system. Once it goes into the nonlinear zone, this superposition rule is not applicable, and we cannot use this kind of a additivity property to find out the total solution of the system. It will only be applicable for the linear system or for a nonlinear system for a small range of motion, as we can see for a simple pendulum. For simple pendulum, it is applicable, but for a small range of vibration. Okay. So in practical application, let us say if I want to model a system, okay, and find a solution. So now I know that, okay, I can model my system in the form of a linear system and then write the solution in this form using the superposition rule if and only if my deformation with respect to the dimension of the system is very small. Okay, if it is higher than a certain limit, the superposition rule is not going to work. So whenever you are doing any practical application of what you are learning in this course, you need to keep in your mind that the range up to which we are seeing the deformation, it is very important to be kept in mind. We cannot ignore what are the limits that the system is going to have, right? Otherwise, you are going to find the solution through the superposition rule, and when you are going to do any kind of a practical testing, or if even if you design a kind of a machine, and if you don't focus upon the linear zone, then it can lead to catastrophic failure of the system as well. Okay, so please keep in mind that this kind of a solution that we will be discussing further in this, like today's live session, it is applicable only in the linear range. Okay, and it is really good in the linear range. It gives a very accurate solution and a very reliable solution. Okay, I hope this is clear. So now I'll be coming on question number 2. So the question says that determine the response of a spring mass system with equation of motion this and initial condition as 0. So see, we already have the equation of motion x dot plus 1.5x is equals to 7.5 plus 4.5 cos of t plus 3 sine of 5t. Now see, this is a linear system. If you apply the homogeneity rule and the additivity rule, you are going to see that it is going to satisfy both of them. That is why I discussed it in the first question. You can use it, and if you'll practice for these kind of equations, then just by merely seeing the equation, you can identify that whether it is applicable or not applicable. Okay. Though that superposition rule and the additivity rule and this homogeneity rule is not important for the questions or for the examination concerned with this course, but it is important for the real life application. Okay, so when you are doing a real life application, then you need to use that rule and keep it in mind when you are mathematically modeling any kind of a physical system. Okay, now if I have this kind of a system, firstly, this is a first order differential equation, right? So for a first order differential equation, what do I do? This is a first order differential equation, and then this is a linear system. So I can simply find out the solution. But the only problem here is that on the right hand side, we have three kind of function. One of them is a constant value. This is a cosine function, and this is a sinusoidal function, right? This is a constant value. This is a cosine function, and this is a sinusoidal function. Okay, so these three kind of external forcing is happening on, is actually being applied on the system, and then now we are supposed to find the solution of this system, right? So we'll use the superposition rule. Since the system is linear, we can use the superposition rule. So what do we do in the superposition rule? We basically divide the solution in three parts. Let us say this part has a solution x1 of t, this part has a solution x2 of t, and this part has a solution of x3 of t. Since the system is linear, we can use the superposition rule, and write the solution, write the total solution as a sum of the individual solution based on the three forcing function. Okay, I hope this idea is now clear, right? Okay, so now first we'll be finding out x1 of t. So for x1 of t, what do we have? We have the equation of the form x dot plus 1.5x is equals to 7.5. Okay. Now, if you look at this equation, and I hope every one of you have gone through the ordinary differential equations. So, when we have such kind of an equation, then we use the rule of solving the ordinary differential equation, wherein we try to find out the particular integral, and and on the basis of the particular integral, we then find out the solution. So, basically, this equation is of the general form x dot plus p of t into x is equals to q of t, right? Wherein p of t is 1.5 and q of t is 7.5, right? So if this is the case, for this kind of a equation, we used to find the integrating factor as e to the power integration of p of t dt, right? This is how we used to find the integrating factor. Now, if I want to find out the integrated factor for this equation, what is it going to be? It's going to be e to the power 1.5 dt, which is going to be e to the power 1.5 t. Okay. Now, since I have the value of integrating factor, after this step, we used to write the solution, okay, by the form something like e to the power minus 5 of t into x equal to integration of 7.5. Okay, I should write it in generalized form over here. It should be I f into x, and this should be equal to what? I f into q of t dt. Okay. Now, if you look over here, that why do we write it in this form? So, if in this equation I multiply e to the power 1.5 t with the whole equation, so I'm going to get e to the power 1.5 t into x dot plus e to the power 1.5 t into 1.5 x is equals to 7.5 e to the power 1.5 t. Okay. If you look at this, if you look at this can actually be written as dy dt of e to the power 1.5 x, right? If you elaborate this, what are you going to get? You're going to get 1.5 e to the power 1.5 x plus e to the power 1.5 x dot, right? This is same as this. So that is why, and then here you are going to get 7.5 e to the power 1.5t. If you take the integration on both sides, you are going to get something of this form. Okay, so we can directly apply it. We can directly apply it, and then we are going to get e to the power 1.5t into x will be equal to integration of 7.5 e to the power 1.5 t dt. So this will give e to the power 1.5 x equal to 7.5. Integration of e to the power 1.5t is going to be what? E to the power 1.5t divided by 1.5 plus c, where c is what? C is the constant of integration. Constant of integration. Now this can be written as, from here, x, which is a function of time, can be written as 5 e to the power 1.5t will get cancelled by what? This, because it will come on the right hand side as negative. So plus and minus is going to be 0. E to the power 0 is going to be 1. So 5 plus c e to the power minus 1.5t. Okay. Now if you look over here, this term is going to decay with time. This term is going to decay with time, and we are concerned about finding out the steady state solution. So we get x1 of t as nothing but 5. And let us say it is equation number 1. We have x1 of t as 5. So we have one solution out of the three. Now we'll go on to the second one, for which the differential equation is going to be x dot plus 1.5x is equal to 4.5 cos of t. 4.5 cos of t. 4.5 cos of t. Okay. Now, first I'll discuss some theory part. I'll not go into depth much, but I'll just discuss from above only. So if you look into the textbook also, you're going to find this equation. I'll just briefly discuss it. It's like, if I have an equation of the form x dot plus ax is equals to b cos of omega t, b cos of omega t, then its solution is written as x is equals to capital X cos of omega t minus phi. Capital X cos of omega t minus phi, where x is going to be the amplitude and phi is going to be the phase difference, right? Phi is going to be the phase difference. So in this case, if I want the values of capital X and phi, so capital X is basically b divided by under root of a square plus omega square, and phi is tan inverse of omega by a, where omega is forcing function and a is basically the stiffness of the system. Kind of stiffness, we can say. Not exactly stiffness over here, because here you can see that the differential equation is a first order system and we are not talking about the second differential. But you can consider it with the analogy of a second order differential equation, right? So this is the form. Now, using this, we can write the solution. Using this, we can actually write the solution, right? So for this equation, First, for this equation, we have B as 4.5, omega as 1, and A as 1.5. So this gives capital X as 4.5 divided by under root 1.5 square plus 1 square, right? So this is going to give us 4.5 divided by under root of 1.5 square is going to be 2.25 and plus 1 3.25. So this will give us the final value. I have done the calculation as 2.4961. This is going to be the amplitude. And phi is going to be tan inverse of, it was omega by A. So omega was 1 and A was 1.5. So if you'll evaluate this, it is going to come out as 0.588 radians. So finally, combining everything, x2 of t can be written as 2.4961 cos of t minus 0.588. And this we'll consider as equation 2. As equation 2. Okay. Now similarly as we did for the cosine function, if I have the equation of the form x dot plus ax is equals to a sine of omega t, something like this, then we have x as x cos, okay, let us say this is not capital X, this is y cos of omega t minus theta. And here the only difference is that y is going to be a by under root of a square plus omega square, and phi is going to be the same as tan inverse of omega by a. Tan inverse of omega by a. So the equations is almost similar, right? The only difference is that the forcing function amplitude in capital X and capital Y are getting changed, right? So now for this, using this, we have the third equation as x dot plus 1.5x is equal to, let me just check, 3 sine 5t, 3 sine of 5t. So here we have a as 3, omega as 5, and a as 1.5. So then capital Y is going to be 3 by under root of 1.5 square plus 5 square, which will come out as 3 by under root of 25 plus 2.25, 3 by under root of 27.25, and this will give us a final value of 0.5747, and phi is going to be tan inverse of omega 5 by 1.5. So this will give us 1.2793 radian. Okay. So combining all this, x3 of t can be written as 0.5747 sine of 5t minus 1.2793 And this is the third equation and also the solution for sinusoidal forcing. Here it should be not cos but sine. So now combining equation 1, 2 and 3, the final solution of the system is obtained as x of t can be written as, so first one was 5 plus 2.4961. Okay, I'll just write 5 plus 2.4961 cos of t minus 0.588 plus 0.5747 sine of 5t minus 1.2793. So this is the final solution. Okay, so now since you have this equation now, if you have any question of the form that you need to take out the response of the system corresponding to any time t, let us say 10 seconds, 20 seconds, or maybe in 10 minutes, 20 minutes, then what you have to do is simply replace t by that value of time. Simply replace t by that value of time and you are going to get the exact position of the system. Okay, I hope this is clear. Coming on to question number 3, we have a spring mass dashboard system with mass 10 kg, stiffness 1000 Newton per meter, and damping constant 100 Newton second per meter. If a periodic excitation of F, which is equal to 10 plus 20 sine 2t and 30 cos 3t, then find the steady state response of the system. Is applied. Okay. So now see, now we have a spring mass dashboard system. In the earlier question, we were having a first order differential equation. Now we have a spring mass dashboard system, so definitely we are having a second order differential equation, right? So the solution, we are still going to apply the superposition rule, but this time, whatever the equations that we discussed in the previous one is not going to be used. We need to find out the solution corresponding to a second order differential equation, and how are we going to get the solution? Okay, let us discuss it step by step. First, we'll write the equation of motion. So we have mass as 10 kg, K as 1000 Newton per meter, and C as 100 Newton 100 Newton second per meter. Okay, so we can write the equation of motion as 10 x double dot plus 1000. Okay, we should first write the damping term, 100 x dot plus 1000 x is going to be equal to 10 plus 20 sine of 2t plus 30 cos of 3t. Okay, so step by step we need to find out the solution. So let us say that the solution corresponding to this is x1 of t, solution corresponding to this forcing is x2 of t, and the solution corresponding to this is x3 of t. So for the first question we have 10 x double dot plus 100 x dot plus 1000x is equal to 10. So if you look over here, what is the kind of system that we are having? We have spring, dashpot, a mass, right? And then a force F is acting on it. Now, if this force F is actually constant, which is equal to 10 Newton, the question is that what is going to be the steady state behavior? So it is very clear. We don't need to, solve the differential equation and then get the solution. By intuitive understanding, we know that if we have a spring mass dashpot system, and then if we apply a constant force on it, what is going to happen? What is going to happen? See, it is going to show some transient vibration, and then it is going to achieve a steady state value, which is going to be constant, right? Because at any point at the steady state, we are going to have a kx balancing f. So x is going to be nothing but a constant, right? It is going to be a constant. So we can simply find out the solution x1 of t by using what? By using the force and the value of the stiffness, right? So if this is k, you can simply write x1 of t as f naught. Let us say this is f naught divided by k, which is 10 divided by 1000, and the value is going to be 0.01. 0.01. Definitely F is in Newton. Okay. So x1 of t is going to be 0.01 and it will be constant over time. Now considering the second equation, which is 10 x double dot plus 100 x dot plus 1000 x is equal to 20 sine of 2t. First, second. Now for this, we have a spring mass transport system with a sinusoidal forcing. Or we can say that for this case, it's a harmonic forcing. Now, if we had to find out the solution, the total solution, we would have incorporated the transient as well as the steady state vibration, right? But it is specifically mentioned in the question that we need to find out only the steady state response. So this makes our life easier, okay? We need to find out only the steady state response. Now, for a differential equation, we basically solve this kind of question or this kind of equation, which is a second order differential equation, by finding the complementary function and the particular integral, and then that is going to give us the whole solution. Now, if you remember, the complementary function was basically concerned about the transient vibration or the transient response of the system, and the particular integral was concerned about the steady state response or the response of the system because of the forcing of the function. So the transient response fades with time because of the damping present in the system. So we are not concerned about the complementary function. We only care about the particular integral for the system, for this second order differential equation, ordinary differential equation to be precise. Okay. So if you want to find out the particular integral, we can do how the equation says that we need to take the denominator, we need to write x double dot in terms of d, like d square, d and everything. But we'll not discuss that over here because we have already discussed about how to solve the solution for a system when it has a harmonic forcing. So for this kind of a system, we can write it in a generalized form, right? We can write it in a generalized form. How? By writing it something like x double dot plus 2 eta x dot plus omega n square x is equals to f sine of not 2 omega t. Right? We can write it in this form using the non-dimensional terms. And for this kind of equation, the solution is going to be, for this kind of an equation, the solution is going to be what? The solution can be written as x of p, which is because of the periodic solution, f naught by k, or here we can say f because we have already used f naught, under root of 1 minus r square whole square plus 2 eta r whole square sine of omega t minus phi. Sine of omega t minus phi. Right? So basically it is of the form x sine of omega t minus phi, where x is this term. X is this term. Okay. Further, phi is, which is the phase angle, it can be written as tan inverse of 2 eta r divided by 1 minus r square. Okay. Now, over here, r is the frequency ratio, which is omega by omega n. Then, okay, maybe I should write frequency ratio. Then eta, which is the damping coefficient. It's given as C by Cc. Okay, so Cc is critical damping value. Critical damping constant, written as twice of under root mk. Okay, so we need to find out these values so that we can put it in the above equation, right? So we have mass as 10 kg, stiffness as 1000 Newton per meter, and damping constant as 100 Newton second per meter. So omega n is going to be nothing but under root of k by m, which is 1000 by 10, 10 radians per second, omega n. Then cc is twice of under root mk. This will be 200. So eta, which is c by cc, can be written as 100 by 200, which is 0.5, which is 0.5. Other than that, the frequency ratio R is omega by omega n. So with for the forcing that we have over here, we have omega as 2. We have 2 by 10, 0.2. Now we have all the values. We just need to put it in the equation. So for x, we have f by k, where f was 20 by k 1000 divided by under root 1 minus 0.2 square whole square plus 2 eta r square. This will come out as 0, 0.02 divided by 0.02 divided by, here we'll have 1 minus 0.04, which is going to be 0.06 whole square plus 2 into 0.5, which is 1 into 0.2, 0.2 square. So this will come out as 0.02 divided by, the final value is going to be 0.98. This will give us 0.0204. Then for phi, we have tan inverse of 2 eta r divided by 1 minus r square, which is 0.2 square. So this is going to be tan inverse of 0.2 divided by 0.06. This will give the value as, I've already done the calculation. Let me see. The value will come out as 0.2054 radians. So the final solution for the sinusoidal forcing term is going to be x2 of t as 0.0204 sine of 2t minus 0.2054. Okay, I hope this is clear. The first one, yeah, this is x of t. Now in the third part we have 10 x double dot plus 100 x dot plus 1000 x is equals to 30 cos of 3t. 30 cos of 3t. Now this can be written as x double dot 2 eta x dot omega n square x is equals to f cos of omega t. Now for this kind of a harmonic forcing, cosine function harmonic forcing, we can write the solution as x3 of t y cos of omega t minus theta, y cos of omega t minus theta, and the only difference over here is going to be of this cos. Other than that, y is going to be same y, okay, f divided by k whole divided by under root of 1 minus r square whole square plus 2 eta r whole square, and theta is equals to tan inverse of 2 eta r by 1 minus r square. So we have already calculated the value of eta. We have already calculated the value of omega n, and we already know the value of, yeah, f. We know in the equation. The only thing that is going to change is the value of r. Now r is going to be 3 by 10, 0.3. So now capital Y is going to be 30 by 1000 divided by under root of 1 minus 0.3 square whole square plus 2 eta r square. Okay. So now when we compute the value, which is going to be 0.03 divided by, we'll have under root of 1 minus 0.09, so 0.01 square plus 0.3 square. Okay, so this will turn out as 0.03 being divided by 0.9582. It will turn out as 0.0313. Similarly, for theta we have tan inverse of 2, 0.5 to 0.5 into 0.3 divided by 1 minus 0.3 square. This is going to be tan inverse of 0.3 divided by 0.01. So the value of theta is going to be 0.3185 radians. So finally, x3 of t can be written as 0.0313, not sine, this is going to be cos of 5, no, it's not 5, it's 3. 3t minus 0.3185. So this is going to be the third solution. So finally, total solution x of t can be written as x1 of t plus x2 of t plus x3 of t, which we'll get by combining all the three. 0.01 plus 0.0204 sine of t sine of 2t minus 0.2054, 2t minus 0.2054 plus 0.0313 cos of 3t minus 0.3185. This is the solution of the system at any time basically the steady state solution. Okay, I hope this is clear. Now, similarly, we have an application based question. So, if we have a slider crank mechanism of this sort, right? If we have a slider crank mechanism of this type, and this slider crank mechanism is basically connected to the mass through a spring and a dashpot, right? So the Y motion of the slider crank is going to act as what? It is going to act as a base excitation for the mass, correct? It is going to act as the base excitation for the mass. So basically we have a spring mass and dashpot system which is connected to a base, and that base is oscillating depending upon the movement of the slider and crank. Now, if you remember that for a base excitation, the base is going to apply a force to the system by what form? By because of Kx and C x dot, right? In this case, x is not like x is going to be y because x is the movement of the mass, right? So basically, our system is going to be of the form mass, spring, dashpot connected to a base which is getting excited. This is y. This is x, y of t, right? Now, the force that this excitation is going to cause on the spring mass dashpot system is what? The force is going to be k into y of t plus c into y dot of t. Okay, this kind of a forcing. Okay, so and for the spring mass system, we have to write mx double dot plus cx dot plus kx is going to be equal to F. Okay. Now, we first need to find the equation for capital F so that we can find the solution for mx double dot plus cx dot plus kx. Okay. Now, see, as it was discussed also earlier, that F could be any kind of forcing, right, with respect to time. But we have the power that we can write this F in terms of infinite series of harmonics, right, using the Fourier transform. What we were doing in Fourier transform, we were having a signal, which was a forcing signal, and we were writing it in terms of the series of sines and cosines. So basically, we were converting that into a sum of harmonics because we know the solution that the system is going to have if there is harmonic forcing. So if I convert my periodic forcing into harmonics, it will make easier for me to find out a solution, right? Because even for ordinary differential equation, we cannot find the exact solution for any arbitrary kind of forcing, right? To find the particular integral, we have some 3 to 4 types of f for which we can find the solution. So for any kind of arbitrary function f, what do? Either we convert, like find the solution, doing a very big mathematical procedure and get into mathematics and find. But as a mechanical engineer, that is not our work. We are not concerned about mathematics as much as we are concerned about a mechanical system. And so what we can do is we can use the easier way out. We can convert that arbitrary forcing as any of these four kind of forcing. And that advantage is given by the Fourier transform. That periodic arbitrary forcing can be converted into a sum of harmonics by the Fourier transform. Now using that harmonics for every harmonic forcing we can find the solution, and by using the superposition rule we can just sum it up. Similarly, that is what we are going to do over here. We are going to y of t. We are going to find the y of t. Okay. So for now, let us consider that y of t is periodic, but I don't know what is the form. So what am I going to do? I'm going to use the geometry to find out the y of t. Okay. So now see over here. Y of t is going to be what? Now, y of t is essentially going to be r minus r cos of omega t, right? R minus r cos of omega t r minus r cos of omega t plus L minus L cos of phi. This is your phi. L minus L cos of phi. This is very simple. Okay. Now, what we can do is we can write cos of phi in terms of what? Sine. In terms of sine. So this can be written as r minus r cos of omega t plus L minus L under root of 1 minus sine square phi. L minus L into 1 minus sine square phi. Okay. Now what do we know? We know that L into cos of phi, not cos actually, sine. L into sine of phi is equal to what? R into sine of omega t. It is always going to satisfy because this, if we make a straight line over here, this is what we are going to get. This length, we are using this length to equate these two equations. Okay. So from here, what do we get? We get sine phi, it's R by L sine of omega t. Now we can replace it in the above equation. So what are we going to get? Y of t can be written as r minus r cos of omega t plus L minus L under root of 1 minus r square by L square sine square of omega t. Sine square of omega t. So if we assume that this value is small, we can basically write 1 minus r square by L square sine square of omega t to the power 1 by 2 is nearly equal to 1 minus r square by 2L square sine square of omega t. So if we put it in the main equation, what are we going to get? We are going to get y of t as r plus L minus r cos of omega t minus L into 1 minus r square by twice of L square sine square of omega t, right? Sine square of omega t. This can be further written if you want to eliminate the square term. See, because we want it in terms of the harmonics, right? We want it in terms of the harmonics. Now, sine square t, we know that there is a relation by which we can replace sine square of omega t in terms of cos twice of omega t. So we'll use that relation. We will use that relation, and then we are going to get what? R plus L. And we can just let it be. Okay, let us just write as of now. R plus L minus R cos of omega t minus L. And then over here, what are we going to get? We are going to get plus L by 4 R square by L square into, not into, minus L by 4 R square by L square cos twice of omega t. This is going to get cancelled with this, and final equation of y of t can be written as R minus R cos of omega t is L by 4 R square by L square. Okay, maybe we can write it. I'll just skip one step. 1 minus this R square by L square into 1 minus cos twice of omega t. Okay, now if you look over here, you can see that we already have function y of t in terms of what? In terms of forcing. Sorry, not forcing, harmonics. We have terms that are constants, and then we have terms that are related to cos of omega t and cos twice of omega t. Anyways, it is of the harmonic form, and we can use every single term in order to find out the final solution. Correct? Now it has become easier for us. So now, if we write the final equation, which was mx double dot plus kx plus cx dot is equal to ky plus cy dot. What are we going to get? Okay, maybe I should use another slide. We are going to get mx double dot plus cx dot plus kx is equals to k into y of t, which is going to give us k r 1 minus cos of omega t plus k L by 4 r square by L square 1 minus cos of twice of omega t, right? Other than that, we have c into y dot, which is a differential of this above term. Okay, so if we differentiate it with respect to time, okay, so what are we going to get? What are we going to get? Plus c r omega sine of omega t plus c L by 4 r square by L square. Then we have twice of omega into sine of 2 omega t. Okay, we have simply differentiated the y of t and multiplied it with c. So this is essentially our equation of motion. Now if you look over here, we have the equations in such a way, like the forcing in a way of we have a constant, then we have cos terms, two cos terms, and then we have two sine terms, which is like a Fourier series, right? Which is like a Fourier series up to order 2. Okay. So over here, what are we going to do? We are going to find the solution at every for every kind of forcing, and then we need to sum it up, right? So this is a very mathematically elaborative question, so I'll not get into finding the proper solution by solving it because you people can do it. Now it's a simple integration, but I'll just give an idea. Like for example, we are going to divide the solution in three parts. Okay, so there are six terms in total. We are going to divide the solution in three parts. One solution is going to be because of constants, and for constants there are two terms. So every part is going to have two solutions, and then we have three parts like this. So we are going to get in total six solutions, which we need to add to get the final solution. So solution for the constant term, which are Kr and KL by 4 R square by L square. How are we going to find out? So we can find out solution as x of t f naught by k, right? Simply f naught by k. For f naught we have kr, and this both you can use. Alright. And we are concerned about finding only the steady state solution as of now. If we had to find out the total solution, we would have to find out everything. But for now, we'll say that we have to find out only the steady state solution. So x of t is going to be f naught by k, which is for the constant term. Now when we have to find out the solution for the, here we are going to get two solutions, x1 of t and x2 of t. Now when we have to find out for the sinusoidal term, what is going to be the solution? The solution is going to be x of t as x cos of omega t minus phi s. Phi s for sinusoidal, phi c I'll use for cosine, where we have x as nothing but f naught divided by k minus m omega. Okay, maybe I should use capital omega over here because omega we have already used. Omega t k minus m capital omega square whole square plus c square capital omega square, this whole to the power 1 by 2, and phi naught is equals to tan inverse of c capital omega divided by k minus m capital omega square. Okay, I hope this is clear. From here we are going to get two solutions, x3 of t and x4 of t. Okay, last is the solution for the cosine term. Now this is easy. Solution x of t can be written as y cos of omega t minus phi c. Again we know capital Y is going to be nothing but f by under root of k minus m omega square whole square plus c square omega square, and phi c is going to be tan inverse of c omega by m minus k minus m omega square. From here we are going to get x5 of t, x6 of t. C, for the sinusoidal term, I should write the terms over here. So the first term is going to be CRW sine of omega t, and then we have CL by 4 R square by L square 2 omega sine of twice of omega t. These are the sinusoidal terms, and then the cos terms. We have K R cos of omega t and KL by 4 R square by L square cos of twice of omega t. So the final equation for the solution can be written as a sum of every single that we have obtained. Okay, this was because of constant, this was because of sine, this was because of cos, and this is going to give us the final solution. So I'll not get into deriving every single term that you people can do on your own, and that will be a good exercise for you as well. But this example I took just to give a basic understanding that if we have a system of this type, which is somewhat related to a physical system, then how are we going to get the solution? So this is how we are going to get the solution. We'll use that physical system. We are going to derive the equation in this form, right? Because we are concerned about the linear range over here. So for the linear range, we can model any of the system as a spring mass dashboard system, and then we can define the forcing in terms of, like, it will depend upon system to system. Like for the slide mechanic mechanism, we used these equations to define y, and then from y we define the force that the base is going to cause on the system, and on the basis of that we found out the solution. Okay, I hope this is clear. So this was just to give a basic understanding. Now, you know, luckily over here, what did we get? We get the forcing in terms of the sinusoids only, like in terms of the harmonic functions, right? So this was easier for us because it was in terms of the sinusoids and cosines. If it would have been something else, then we need to use the Fourier transform, convert it into a series of sines, cosines, and constant values, and then you know how to deal with the question. Now the question is up till what number we should convert any kind of arbitrary signal into the Fourier transform. So that is up to you. That is up to you, because what happens is that as the frequency increases, right, the effect or the amplitude decreases. So if we have a, let us say, forcing in a way that for the first omega, we are having the amplitude as, let us say, 1. For the third, or let us say 3 omega, we are getting amplitude somewhat 0.2. We don't need to calculate the fourth one. 0.2, we have already come to a very small value. As compared to 1, 0.2 is very small. Not very small also, but it is small. If you are doing hand calculations, we can neglect above it. If you are doing calculations on software, we can then still consider 3 to 4 more values. And what you can do is you can interestingly also simulate this in MATLAB and see that up till how much value we should consider, so that it does not cause any kind of a, you know, a very big change into the system. Okay, I hope this is clear. Now we'll get into the next question. Yeah, which is about the Fourier transform itself. Now, So by Fourier transform, what we are trying to do is we are going to find out that if we have a function which is in time domain, how do we convert it, or what are we going to get in the frequency domain? Because we don't know how the system is going to behave, right? For example, if I have a time response, okay, arbitrary time response, let us say. So if I have a time response of this type, it is easier for us because we know this is periodic. We can find out this time and then find the frequency. This is time, this is x. We can simply find out this and find f as 2 pi by t, right? Okay, this is going to be omega. So then we can find f also. F we know it is going to be what? Since omega is 2 pi f is going to be 1 by t. So we can find out the frequency. But now if I have something of this type, actually it is also easier because here also we can calculate the time period. But what is important over here is that what is important over here is that this is not a pure sinusoid or a cosine function, right? So then in Fourier transform, what do? We convert it into pure sinusoids and cosine forms, and so that we can sum it up and give it as a function of those. Now for this kind of a function, if I need to find out the Fourier transform, if I find out the Fourier transform, what I can do is I can convert it from a time domain to frequency domain. And if I can convert it to a frequency domain, what can I know is that what is the contribution of a certain frequency in the system and what is its amplitude, total amplitude. Like for example, there are three frequencies present in this signal. I'm just assuming it. I don't know that. F1, F2, F3. Then these three are going to have some contribution. A1, A2, A3. Then we can use the Fourier transform in order to get those values and then we can plot it, right? So here we are trying to find out the Fourier transform of cosine and sine function. So for a cosine function, let us say that x of t is given as an cos of 2 pi fn of t. So this is a cosine function. Now what is going to be its Fourier transform? FFT plot. See, this is a cos function we know, right? Now you can see also that how do we obtain it, but over here I'm just going to write this thing that for a function of the form a e to the power I 2 pi fn t, a e to the power 2 pi fn t, comma, the ft is a delta f minus fn, a delta f minus fn, where delta is nothing but the Dirac's delta function. Dirac's delta function. Okay, a into delta of f minus fn. Okay, now if I try to find out the Fourier transform of this, what I know is that any kind of cos function, it can be written as e to the powers, complex powers, because we know e to the power I theta is cos theta plus I sin theta. E to the power I theta is cos theta plus I sin theta, right? So what I can do is I can assume x of t as, so basically cos of theta can be written as e to the power I theta plus e to the power minus I theta by 2, because we have cos theta plus I sin theta, and then this e to the power minus I theta is cos theta minus I sin theta. Okay, so if we sum these up and divide it by 2, we are going to get cos theta. So we can now write x of t as what? We can write x of t as 1 by 2 into e to the power I 2 pi fn of t plus e to the power minus I 2 pi fn of t. Clear? And this should have an an. Okay. Now if you look over here, if you need to find out the Fourier transform, what are you going to get? Firstly, the Fourier transform of this is going to be what? It is going to be it is going to be delta f minus fn, and for this it is going to be delta delta. For this it is going to be delta, yeah, I hope I'm right, yeah, minus f plus fn. Okay, then we have it multiplied with an by 2. Okay, so for the previous case, if we would have plotted it, if we would have plotted this, what do we get? We have the frequency axis, and then we have the x, which is a function of frequency. Usually we write it as capital X, and we're going to get this, which is going to have a height of a, and this value is going to be fn. So for this, if we compare, we have an by 2, and then we have one as f minus fn and one as minus f plus fn. So if this is the amplitude, which is a function of frequency axis, and this is the frequency axis, we are going to have two peaks like this and like this, where this is an by 2 and this is an by 2, and this is fn minus fn 0. So this is going to be the plot of the Fourier transform. Okay, I hope this is clear. And the contribution is half half. The contribution is half half. Now this was for the cos function. This was for the cos function. I have to find out for the sine function as well. Just a second. We have to find out for the sine function as well. So for sine, we can write as bn sine of 2 pi fn of t. Now, similar to how we wrote cos theta, we can write sine theta as, we can write sine theta as e to the power I theta minus e to the power minus I theta divided by 2i. And if I now multiply and divide it with I, we are going to get minus I e to the power I theta minus e to the power minus I theta divided by 2 divided by 2. So what are we going to get over here is that the Fourier transform is going to be minus I by 2 into Bn delta f minus Fn delta minus f plus Fn. So over here, firstly, our response axis is going to be what? Imaginary. The frequency axis, okay, I have to make the frequency axis above because over here we are going to have one positive and the other negative value. Okay, one positive and other negative. Here it should be a minus as well. So the Fourier transform is going to be something like this. Bn by 2 with a minus Bn by 2 Fn minus Fn. Okay, so this is going to be the Fourier transform. But the question is that why do we even bother about Fourier transform? I mean, how do I even care about Fourier transform? So the thing is that if we have a theoretical system, if we have a theoretical system, forcing function, the mathematical form is known, correct? Which we were doing earlier. Or even if we don't know the mathematical form, we were using, like for the slider crank mechanism, we were using whatever we know about the system in order to find out the forcing function in its mathematical form, correct? But when we are talking about a physical system, is it always known to us that what is going to be the forcing? I mean, a system can experience any arbitrary kind of forcing, isn't it? Like, for example, if I have a heavy duty machine, okay, which is showing some kind of a vibration, and I want to damp out that vibration, okay, so I am using a rubber in its bottom in order to cancel out the vibration. So I need to design that rubber in such a way such that the vibration is cancelled out. So if I consider my system linear, I'm going to use the spring mass dashpot system. Okay, and now I need to analyze that. Okay, what should be the values or how the rubber material should be made, what should be its properties, such that its stamping value and the stiffness value is going to be used for getting X, which is the final response to the ground, as very small. Okay, as very small. So for that machine, the forcing that is being or the vibration that is being going into the system is arbitrary. And I don't know. I have no idea about how should I function it. Okay, I just don't know. So then what am I going to do? What am I going to do? All I know is that even if I knew the mathematical form, I used to convert it into Fourier transform, write it in the series of this cosines and sines and constant values, and then using the harmonics, I used to find out the solution. Over here, I don't know the mathematical form. But what I can do is I can operate the machine. I can take out the value. I can measure the forcing or I can measure the displacement. We have many kind of a sensors, like we have the accelerometer, or we have non-invasive kind of sensors like the laser vibrometer, by which we can measure the displacement or the acceleration, whichever we want. So if I'm able to measure the force or displacement, what I can do is I can take the time series data, because these sensors are going to give me time series data. I can take the time series data convert it into like Fourier or frequency domain, into the frequency domain, right? And now we know what, by this plot that I showed you over here, we know how it is working, right? So if I have the time series data, I use some mathematical tool, like we can use MATLAB, and MATLAB has this FFT command which is used for computing the Fourier transforms. So we can use FFT, get the FFT plot. For FFT plot, we are going to get the, like for example, something like this. We can have a dominant peak, we can have the subharmonics, some things like this. Okay, let us say F1, F2, F3, F4, and it will give amplitudes like A1, A2, A3, A4. This is frequency and this is X. So now what I can do? Earlier, I didn't know that how should I model my vibration that I want to damp out. But now I know the frequency, I know the amplitude. So what I can do? I'm simply going to use my understanding of FFT, write it into a series of sine and cosine from this value, from the experimental value, right? And use it in the theoretical system. And use it in the theoretical system. So basically the idea of computing the Fourier transform from an experimental data is because every time we do not have the provision of getting a theoretical equation just by deriving it, right? Sometimes for a practical case, the vibration is arbitrary, okay? And we just, by simply seeing the time response, we don't know how we should model it. So we can use the concept of FFT. From this, we can write it in a series of sines and cosines, and then we can use the theoretical model in order to get the solution. And then by using the solution, we know that, or we can derive, we can get that what should be the, how the double rubber material should be designed so as to get the least possible transfer of the vibration to the ground. Okay, I hope this is clear. Okay, so this is about the campbell diagram, and I think I've missed uh, inserting the figure, so maybe I'll just make it. So we know for a campbell diagram, we have hertz over here, we have motor speed in RPM over here, right? And then we have this, which is going to be 1x, let us say. Okay, so now suppose we are going to have different RPMs of my system. So we need to find out that what is going to be the critical speed at an operating speed of 1800 RPM. So I basically designed the question in this way. This was 0.5x, this was 2x, and then it was something like this. We had 1800 over here. Yeah, on the 2x diagram. Yeah, perfect. Okay, so we have to find out the critical speed. So, basically critical speed was what, right? So we had RPM on one axis, and then we had this frequency on the y-axis, and then there were these lines, right? Slanted lines, using which we knew that the intersection, okay, the intersection of these lines with the natural frequency is going to give us the critical speed. Okay, was going to give us the critical speed, because what was happening? See, on the x-axis, we have the operating speed. Okay. Now, if we don't have any idea about the natural frequency of the system, what we can do is we can give it an operating speed that may result into some very high amplitude oscillation. When we are talking about a motor or any kind of a rotating equipment, considering that we have an ideal system which has homogeneous and evenly distributed mass without any kind of eccentricity, it is actually very difficult. I won't say not possible, but actually very difficult, time consuming, and very, very, very expensive. Okay. Every one of us know that if we get into obtaining a very precise and accurate sample of any kind of a system, the cost increases, right? Because the machining is done on the micron levels to obtain the precise and accurate dimensions. So we usually use a dimension which has some kind of a tolerances. Now, because of those tolerances, it may happen that there is some kind of eccentricity or unbalance in the system. We have already studied that this kind of imbalance in the rotating system is going to cause what? It is going to cause unbalanced rotations, right? Because of the unbalanced masses, we are going to get no, sorry, vibrations, right? And we are concerned about how to reduce those vibrations, okay? Now, in order to reduce those vibrations, the best possible way is that we keep our system away from the natural frequencies. Now you know that a rotor, though we consider it as a 1 degree of freedom system, and then it is going to have a natural frequency. But that is not true because it's a continuous system. And we know that for a continuous system, there can be infinite number of natural frequencies, right? There are going to be infinite number of natural frequencies because there are infinite number of mass points. So we basically, for a rotor, we calculate the first natural frequency, second natural frequency, and like that. And then we see upon making these slanting lines of 0.5x, 1x, and 2x, that wherever this slanting line is matching with the natural frequency, any kind, nth natural frequency, whichever rotating speed we are getting at that point, we are going to avoid it at any cost in order to reduce the vibration or to prevent any kind of catastrophic failure. Even to prevent any kind of catastrophic failure. Because if you'll see into machineries that need a very high accuracy, like if I'll talk about an aeroplane, which has a turbine, right? And then we have a compressor and everything. There, the blades are made with very high precision, and that is the reason that the airplanes are very costly. Because even a very small, even a very, very, very small like eccentricity is going to cause high vibration, a very high vibration, and it is not going to cause, like just vibrations and nothing else. It is going to lead to catastrophic failure. Simple. You can see, actually, you can go and Google also that how for turbines and compressors, even a very small variation of the mass actually leads to catastrophic failure, which leads to a heavy loss of manpower, and assets and cost as well, money also. Okay, so in order to avoid that, it is very important for us to design my system in such a way such that it is away from any kind of a critical speed. Okay, so over here we basically have omega 1, omega 2, and we need to find out what is going to be the critical speed at an operating speed of 1800 rpm. Now, over here you can see that I have made a straight line at 1800. Okay, I have made a straight line at 1800. Now, this value is essentially the critical speed. Okay, but what is this value going to be? What is this value going to be? So if you remember, both the axes were having One was having in rotations per minute, another was having in hertz. Secondly, we know the slanting line is of 2x, which means that for a variation of x in the x-axis, there is going to be a variation of 2x in the y-axis, right? This was x, this was 2x. Then this is known as 2x axis. So for a change of x in the x-axis, there's going to be a change of 2x in the y-axis. Okay. So what do I know? Firstly, we'll convert 1800 into hertz, which is 1800 by 60. And then we have twice of the variation. So this is going to be into 2. 60 hertz is going to be our critical speed. This was simple. This is a very simple question. Now, if someone asks you that if I increase the frequency from 0 to 1800 RPM, let us suppose, because that is how a system works, we cannot directly switch it to 1800. It basically increases with time. So how many critical point it actually encountered in between 0 to 1800? So what do? You start making, like, going over here, 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 and you'll see, okay, there is this one interaction at here. Then you'll go further, and then you'll see there is one interaction over here. And then when you'll go further, you'll meet this line. So basically, before reaching to 1800 RPM, it has crossed two critical speed values. Two critical speed values. Okay, I hope this is clear. And if in the assignment problem there is any question related to the Campbell diagram, you can actually solve it because it's a very simple thing. Okay, the basic understanding is very important. This diagram seems very easy, but the basic understanding behind this diagram, it is very, very, very important. And in industries, they use it very rigorously in order to avoid any kind of catastrophic failure in the system. Okay, now coming on to the last question for today. So we have for a system under periodic forcing, which includes a sum of harmonics, what will be the time period of the resulting vibration? Okay. So see, what we have is for a system under periodic forcing. So let us say my function for the system is something like a spring mass dashpot. F, where F is a sum of harmonics. A1 cos of omega 1t plus A2 cos of omega 2t plus A3 sine of omega 3t. Okay, we'll just consider sine only. Anyways, cos is also fine. There is no issue. Okay. If there is a forcing of this kind, so what is going to be the period of the resulting vibration? Now you see, if I would have only omega 1, the period of oscillation was going to be omega 1. But now I have three frequencies, omega 1, omega 2, and omega 3. So what is going to be the final frequency of oscillation? Since over here we are dealing with a linear system, we'll assume that the ratio of omega 1, omega 2, and omega 3 with respect to each other, they are somewhat like integers only. Okay, it is not a irrational number, because if it would have been an irrational number, it would lead to quasi-periodic motion, which is a complex kind of behavior, and it does not fall under the linear system. It goes into the nonlinear vibration criteria. So for now, we'll suppose that omega 1 is 20, omega 2 is 40, and omega 3 is 60 radians per second, radians per second, radians per second. Okay. So if you look over here, if we try to calculate the time period corresponding to all the three frequencies, T1 is going to be 2 pi by 20, which is going to be 0.3142 seconds. T2 is going to be 2 pi by 40, 0.1571 seconds. And T3 is going to be 2 pi by 60, which is 0.1047 seconds. These are the three time periods. Okay. Now, since we know that the ratios of omega 1, omega 2, and omega 3 are what? Integers. They are integers. Now, what I mean to say by that is, if omega 1 is 20 and omega 2 is 40, so if omega 1 is completing one rotation, let us say in time t1, then omega 2 is completing that in time t by 2. Or what we can say is that t1 is twice of t2, right? Which is also equal to, which is also equal to 3 times of t3, right? So the third response, which is because of t3, if it is taking time t3, 3 times of that is taken by t1, right? So up till the first response completes one cycle, the second one has completed two cycles, and the third one has completed three cycles. Okay. So basically, T1 is going to be the time period of the response because till T1, the first response has completed one cycle, second has completed two cycles, and third has completed three cycles. But combined, we need to find out the combined period now. We don't need to find out the minimum. We need to find out the maximum period. And then this should be what? This should be integral values, right? These should be integral values. So what I'm trying to say is, if I try to plot and show you that what I'm trying to say, so we have like this, and then let us suppose that A1 is greater than A2 is greater than A3. So when T1 completes one cycle, which is this, T1 completes one cycle, T2 completes two cycles. T2 completes two cycles, and T3 completes three cycles. Three cycles, something like this, and then we'll have this like this. Okay, I hope I've tried representing it visually like this. Okay, so what do we get? See, the minimum period, the minimum period is what? T3. The minimum period is T3. But since T3, if multiplied by 3, gets to T1. So what do we know? No, over here. We know that after three cycles of T3, T1 has completed one cycle. Our basic concern is that what is the maximum time period? And the maximum time period is going to be the period of the resulting vibration, because the resulting vibration is going to have three components, and those three components are going to repeat itself. Like T3 is going to repeat itself after every T3. So it has a period, minimum period of T3, but it can have a maximum period also, right? It can have infinite maximum. It can have 2 T3 as a period, it can have 3 T3 as a period, and likewise n T3 as a period. Okay. But we are concerned about that we should always look into the response which has the maximum period. And it should be the integral multiple of all the minimum periods. And if that is the case, then the maximum period is what? It is going to be the period of the resulting vibration. Simple. Okay? I hope this is clear. So that is it for today's live session. And I hope that all the questions were clear. So yes, please go and complete the questions that I have left for the calculation thing. And then, yeah, we'll meet next week. Until then, okay, thank you. Good night.